Okay, so we are still waiting for maybe 20 students. We will begin in 2 minutes. Okay, good afternoon, everyone. So last time we talked about the transport layer, but we just begin this lecture, right? So today we'll finish this slide, and the next is also a transport layer lecture. Okay, so the slides, and we have two parts, basically point 1 and point 2 here. Okay, and today we will have a quiz released on transport layer. Okay, stay tuned and just be aware of this quiz. Okay, it should be a quick one, so we probably would just have a deadline of 1 week, okay, because it's not too many time before the semester ends, so we will not make it too long. Okay. All right. So last time what we see is that so the transport layer, one important task is called a demultiplexing. Right. So basically, if you have multiple apps, right, applications on top of your machine, right? So if you just use network layer, it just care about how to route the packets, or we say the datagram through the network, right? Each individual unit of packets, okay? It doesn't care about which packet is from which application. And the important task of the transport layer is to give the port numbers, okay? So you can see the content of both TCP and UDP has a port number, okay? So port number here. Right. This is really to build the route, right, to the applications on both sides. Right. So this is a UDP, and keep in mind this is called a user datagram protocol. Right. So datagram is like the datagram in the network layer. Okay. And there's also another protocol called TCP, right? So called a transmission control protocol. Okay. Here each packet is no longer called a datagram. Okay. It's called a segment. Okay. Because here in TCP, we have order, and order matters. Right? So one segment of the entire stream, another segment of the entire stream. Okay. So in TCP, we call a packet a segment. Okay. And we talked about TCP, right? So it has a virtual circuit ideas, connections, right? So which means you need to do three-way handshake to establish connection, and when you finish using it, you need to tear the connection down. Okay? Otherwise, it will occupy resources on both sides. And so you also have two concepts, right? One is called the flow control, which is control how fast you can send, because the receiver cannot receive in very fast speeds, and you should send at a slower pace. Okay. Another concept is called congestion control, and we will see that in the next lecture in more detail. Okay. So congestion control thing, even though sender and the receiver can move forward really quickly, but because down there in the network layer, it's hop by hop, right? So in a particular link, maybe there are multiple streams using that link. In that case, there will be congestion. So even though the sender receiver can both proceed very fast, but there's congestion. And in that case, your sender should also send slower. Don't overload the intermediate router, right? Because the router will drop packets, and since it will cause a lot of retransmission, since it will get really slow. Okay? And then we talked about the TCP connection setup, which is through the three-way handshake, right? SYN, SYNAC, and ACK, okay? And we see that, and we have the concept of sequence number that we see before, right? Then we talked about why we need a sequence number, right? So because of the security, okay? And we will see these SYN flood and SYN cookies concept later in the second slide, set of slides. Okay? Another is a TCP, tearing down. Right? If you say I don't want to send anything more, I want to finish this connection, you send a thing. These are all bits in the bitmap. So look at here, we have a flag, right? In the flag, same thing, they are all just flat, 0 or 1, okay, 1 bit. Okay, so when you tear things down, right, so you are just saying, I'm not sending anything, but you allow the other side to continue to send you some stuff before ending. When it's ready to end, it will send you the thing, okay? And then you need to acknowledge it. Because of this reason, you need to wait for maybe 30 seconds, right? Because your acknowledgement to the server, right? Here it's a server. Your acknowledgement to the other party may not be received, right? It could be lost, right? Because the router has a full queue, etc. Right? So you need to wait for sufficient long time, make sure such a acknowledgement will reach the other side, let's say the server. Otherwise, the server will have a half-open connection, right? Which means it will not release its results to communicate with the client. Okay? And similarly, if your server initiated the thing first, right? In that case, so client initial thing is very natural, like you log out. The server may also initiate the thing because the server no longer maybe timeout after 30 minutes. Okay, so the server initiate the thing, then server need to wait for 30 seconds before truly tearing down the connection. Okay, so there will be some lag behind time to make sure the other party receives that acknowledgement. Okay? Otherwise, you think about it, if you don't acknowledge your server, right, it's gone and you tear down, the server will never get a chance to release its results. Okay? And so the sequence number space, right? So in TCP, the sequence number is 32-bit, which is okay, right? So it will wrap around, which means if you go to the 1111, right, all 1 bit, the next number will be 000, or 0. Okay? It will wrap around. Okay, it's like a circular cube, right? So it's, let's say if you're in the field of 7, right? So it's 0, 1, all the way to 6. And then the next one is 0. Right? And yes, there's some reason why we need to choose some random values initially, right? So for multiple reasons. One is for wraparounds, and you don't have some like confusion because maybe that's the previous TCP connections packet that somehow gets stuck and it's finally spend a long time to reach you, but you actually already teared down that connection because of the retransmission of the same packet later, right? And that packet somehow is lingering in the network. Okay, and then you have a new TCP connection which happens to have the same port number and the same IP address. Then there will be confusion. If you use random initial values, then the range is very unlikely to overlap. Otherwise, if you always start from 0, 0, 1, 2, 3, 4, 5, next time you start again from 0, 1, 2, 3, it's always go on the smaller end, right? So very likely the number will collide. So here, that's why we call the TCP packets, right? Remember, so for the network layer, we call the datagram, right? In the so in the TCP, because it's a stream, we call it segments. Okay. So this is because you think about a stream, right? You cut into segments that are ordered. Okay. So we say that byte stream is broken into segments. Okay. So we don't no longer call datagram, we call packets as segments in TCP. Okay. And so the sequence numbers, so the size is limited by a maximum. Let's say a maximum segment size allows. So it's like how large your packet can be, right? Your segment can be. Okay, it has a size limit of your each segment size. Okay. Here is an example, right? So we will have the sequence number, which represents the number of bytes, but the initial one is actually the 0th byte, but we will have a random number. Okay? And then after this length, we will reach this segment number, and then another segment is this number. And this is a little bit longer, another segment like this. But all of them should be smaller than MSS, maximum segment size. Okay. So here is an example of so-called bidirectional communication, right? So here we are saying that each side of the connection can send and receive. Okay. Once you have the TCP connection, it's a bidirectional. This is what we are saying. Right? So you can basically regard it as a actually 2 unidirectional stream. Right? So one is from client to server, another server to client. Again, So we are talking about client server, but in reality, you don't have to be client server, right? Any two pairs that are communicating. So you have two streams, right? One is from, for example, one is client server, another is server client, because they can have different sequence numbers, okay? This stream has one sequence number beginning, and this has another sequence number. Let's take a look at how this process will be looking at. Okay? So let's assume that the sequence number is 1, right? And the acknowledge number is 23, which means acknowledge is this side. So so basically, we are saying that the client choose 1 as an initial. Let me see. So initial sequence number of a client is 1. Okay. Oh, so I should use this. 1 is on this side. Well, the initial sequence number chosen by server is 23. Okay. So that's the concept. So now let's assume that client send a 1,460 bytes from the client to server. So what will happen is that, originally your sequence number 1, now you add so many bytes, okay? So your acknowledgement for the next byte should be 1461, okay? So keep in mind the sequence number is actually in the unit of bytes, how many bytes, okay? But this time, actually your sequence number that you start to send is still 23, right? But what if on the other direction, you send 730 bytes, right? If that happens, okay, so you need to add a 23 with 730. Okay, it will give you 750. Okay? So you can see this direction right now, the progress is to 753. While the other direction, the current progress right now, the next one should be 1461. Okay? And here we see that this is piggyback, right? So data and acknowledgement can be in the same message. Otherwise, you have to send 2 messages, you have the same IP headers kind of twice, okay, and all the other associated. So this is more efficient. And similarly, when you receive this and you also want to send, you can piggyback them together. So in the meanwhile, you acknowledge that you receive, right? And in the meanwhile, you send some additional data. Okay. So here you can send another 1460 bytes, right? And if that happens, right now this is your progress. Okay. This is your progress. Now you need to add to the new stream, and it will become this number, right, that it expects you to have starting from the next one. Okay. Yeah. Any question regarding this? How the sequence number is forwarded and the bidirectional communication? Okay. So then let's continue. So the next concept is flow control. Right? So the flow control answers this question: how many packets should a sender transmit? Right? So really, if you can send super fast, like 100 megabytes per second, but the receiver can only receive 1 megabyte per second, what will happen is that when you send and it's finally you have to stop somewhere, right? Because if you send 100 packets, the receiver can only receive 1 successfully. The other 99 will be dropped, okay? Or will stuck somewhere. Right? The queue will pile up. So the best way not to cause congestion, right, is to send slower, okay? Right. If you have packet loss, then you will introduce additional packets, and the system will get really messy. Okay? So you don't want too many packets to overwhelm the receiver. Right? Receiver can tell you, hey, I can only receive packet in this speed, and then you send also at this speed. Okay. So the size of the receiver buffers can change over time, but overall, the receiver's receiving buffer will be notified to the sender. So the sender knows, hey, how large the buffer is, how fast I can send. Okay. So the solution is to advertise that receiver, advertise the window size to the sender. Okay. Receiver tells the sender how big the buffer is, right? And assume that we have a window of size n, to advertise the window of size n. Then the sender may transmit n bytes without receiving acknowledgement, right? Because if you have not received acknowledgement, which means they are still in transmission, so basically you need to sender need to hold these packets because there could be a retransmission necessary. Okay? These sending messages can time out or can be dropped. Right? And on the other side, the receiver has to receive these packets. Right? So it can only receive those packets. It cannot be faster, which means if your sender send n bytes already, okay, which is the window side, you should now stop. Okay, you should hold until you get enough acknowledgement, then you continue. Right? So the receiver's advertised window controls the speed the sender can send stuff. Okay? The sender can only send the stuff n bytes that are not acknowledged, okay? Not beyond that. Okay? This holds the sender sending speed. Okay? After each acknowledgement, the window will slide forward. Right? If you receive a segment, then you know that the content is -1 second. You can send another segment. It's like this. This strictly limits the sender's sending speed. And the window may go to 0. So, for example, the receiver really kind of cannot receive anything or gets stuck, then it will advertise 0 to you. Okay? So where is this advertised window locate? Where does the window locate in the packet? Right? So basically your sender was something like this. Right? So the receiver window will be here. Okay, you see this window field, 16-bit. Okay, so this is the window size. Okay, which can be written by your app. Let's say, hey, I want to receive at this speed. Okay, and so let's assume that this is the stream that you're sending. Okay, this arrow. You can know the stream direction. Okay, and assume that your received packets tells the sender that, hey, I acknowledge this guy, this segment. Okay, and meanwhile the window, I can go with the window size, right, to here, okay, to the blue dot. Okay, but right now the sender is sending, right? So the sender can only send, let's say these are unacknowledged, right? So sender can continue to move to here, right? But you cannot go beyond. You can continue to send, but even if you have more content here, you cannot go beyond this point. Okay, right? This allows your window to hold your sending. Okay, unless let's say this acknowledgement number is plus some bytes, that's the sequence number plus. Then if you move on this direction, this bound can move onwards for this direction. Okay, but you keep this sliding window so you don't oversend stuff. Okay, you send only so many unacknowledged packets, and then you hold. This is called a flow control, right? So the receiver gives feedback to the sender side with the acknowledgement number and how large your window can be. The sender will send until the window size, and that's it. Any questions? And the window actually can change its size. We will see later in TCP that this window size will be changed. Okay, so what we do here is actually, this is the received packet, right? You can keep receiving from a receiver. Each time the window size may slightly change. Okay, you can update the window size. So these packets must be buffered, okay, on the sender side, because who knows whether you will, because they are unacknowledged, maybe they're lost, right? So you need to retransmit. So you have to keep them in your memory of the sender. But here, those packets you can drop, okay, because there's no way that you will need them anymore. It's already delivered to the upper level protocol or the application. Okay, so here, oh, sorry. So this is app, right? So I think this diagram I explained wrong. This is your sender side application, right? Application is saying, I want to send this, application side say, hey, this is a program running on it. It says, I'm appending stuff to the stream, right now append here, okay? But this window stopped here, okay? Right. So these are to be sent. You cannot send it to here. Right? Otherwise, you will have more than the window size or unacknowledged packet, okay? So what I previously said is here is actually here, okay? This is a content provider app, okay? Of course, if the app is writing content to your stream really slow, then probably it's here, then you just go to here. Right? But in general, the app writes much faster than a network. Okay? I hope this is clear. So let's take a look at the sliding window example. Let's assume we have a packet here, right? And you segment into 3, okay? First, second, third, okay? And the first will acknowledge, the second will acknowledge, the third will acknowledge, okay? So what happens is the moment you receive the first segment is acknowledged, right? That means your window size is 3. Right, now the first is acknowledged, I can go to 2, 3, 4, okay? And once the second is acknowledged, like here, right, then you can go to 3, 4, 5, okay? So you can send another 5. And similarly, when the third, 1, 2, 3, right, the third is acknowledged, you can send 6, right? Because, you know, so you can see that strictly speaking, each time you only have 3 frames, 3 segments on the fly. Okay? You will not have 4 on the fly. So it limits how fast the sender can send, depending on the receiver speed. So let's assume that, hey, this time, this packet is lost, okay? Right. So if this is lost, then we can acknowledge 4, we cannot acknowledge 5, right? Okay, and we will acknowledge 6. Right. And by that time, we will say, hey, 5 is not received, I'm still acknowledging 4, okay? And even 7, I'm still acknowledging 4, and no, here I'm still acknowledging, okay? So sender side will time out. Basically, if you didn't receive the acknowledgement for a while, it will time out, and then you will resend files. Okay? Because so far, you know that all the way 1, 2, 3, 4 are coming, because it's sending them. But from 5 to 7, you have not received a 5. So no matter how many others you receive, you should start from 5. It's a string. So by that time, you will resend these 3. Hopefully, this time, nothing is lost. It is okay? And you can see this diagram, you have an arrow downward, right, for the time. So that's why this slope decides how fast the sending can respond. The speed in the median is the same. So the slope is similar. Yeah, so then you can acknowledge hopefully all of them out. Right? Okay. And TCP is acknowledge clock. Right? So for example, here, if you have this, and after a while, student receive it, you will send it again. Okay. So the short round trip time, RTT means round trip time. Right? So is this time basically. Okay. You go there and then acknowledge back. This is round trip time. Okay. So if you have a shorter round trip time, you have a quicker acknowledgement, right? This packet is acknowledged faster. So the window slide quickly. Okay, slide. On the other hand, if you have a long RTT, right, so your 2 communicating parties are very far away, then you will have window slide slowly. Okay. I hope this is very intuitive. So so we talked about the receiver need to acknowledge to receive the packet, right? So what should the acknowledger be doing? Okay. So here are the steps. You need to acknowledge every packet, right? So because you want to make sure every packet is received. And you use so-called accumulative packet as acknowledgement, right? So the acknowledgement means all the way to sequence n, less than sequence n has been received. Right? So for example, if you go here, I can acknowledge all the packets since 1, 2, 3, 4 are received, but 5 is not received. So when you acknowledge 7, you're still saying, hey, 5 is not acknowledged, only 1, 2, 3. And the 7, even though you are saying, hey, 7 is received, but your window stops. The beginning of the window is not 5. Okay, so you can still just acknowledge 1, 2, 3, 4, acknowledge 4. Okay, it's a cumulative concept. Right? So when you have a sequence number n, it implies that in the acknowledgement, your sequence number is n. It implies acknowledgement for all the sequence numbers, the bytes that have been received less than n. Okay, it's a cumulative. And you can also use a so-called negative acknowledgement, indicating which packet did not arrive. Okay, so for example, you can say, hey, 5 is lost, it's not arriving. Right? And you can also use a so-called selective, right? So indicating, hey, So 5 is not received, but for example, you say, hey, I received 6, I received 7. So this is actually an extension of TCP, because if you can acknowledge, hey, 6 and 7 are properly received, you probably can skip the retransmission 6, 7, because they're already on the receiver buffer. Okay, it's a out of the order receive, right? You can first hold the late packets and then wait for the early. Okay, so these are the concepts. So the selective acknowledgement stack is an extension of TCP. But so it will be out of order, but you are first receiving those late packets. Then once the first packet arrives, then you move the window forward or by a big step. Okay? Something like, let's say you have 5, 6, 7. Right? So I can first acknowledge 7 as 6 and get back in. Once 5 arrives, I move it by 3 to 8. So this is okay. If you enable that extension, of course. And yeah, so this is just a repeat. And there's a steady window syndrome. Right? So what is that? Right? So if your window size is very small, right, it will be very undesirable. Okay. So this is because whenever you send stuff, it's not just your data payload that is there. Okay, there's a lot of headers. Okay. So if you have very small packets, very small content, okay, the headers will dominate the data. You think about it. Right? So you have the port number, so you have the IP address, you have the Ethernet MAC address, etc. Right? All these contents are there, but your data is just a little bit. Right? So you can see utilization is very low. If you send 1 byte, you need maybe 120 bytes of header. So this is called silly window syndrome. Okay, multiple small packets is not desirable because then you are most of the bandwidth is used by header. Ideally, your data should be much larger than header. Header can be ignored. This is just like in your operating system, right? So you have the file, but you really don't count the file metadata, like the file name and the footprint of the, like how large your file is, right? What's its path, etc. These metadata, of course, they consume space, right? But you usually don't count them. Okay. But actually, they are there. So it's occupying some operating system space. So the equivalent problem is saying that, hey, the sender should transmit packets not 1 byte at a time. Okay, if it's 1 byte at a time, but you attach many bytes of header, this is going to kill the performance. Okay, so what we do is, hey, if we have a stream of data, the string length means the length of the number of bytes in the data. Okay, so what we will do is we can do this, right? We can write to the socket 1 byte at a time. Okay, but actually it will not just when you say write, it will not just call the network interface card to send it. It will buffer. So how it works is this, right? So if your window size is larger than the MSS, right? So the maximum allowed packet size, and the available data is also larger than that. So just to send the data. So here the data is not the data that you just write for 1 byte. Okay, it's the data that you append so far, right, in the window. Okay, if it's large enough, you just send using maximum segment size. Right, that's most efficient. Right? So you fully utilize the data segment. Make sure the whole packet is MSS in size. Okay, and so otherwise, right? So you will see if there's an unacknowledged data, right? So then you have to enqueue that in buffer, right? And so basically we are saying that so how to say this? So you need to wait for the acknowledgement, right? When you send, okay, when you send in the buffer. So here's what we have here. When you send, like in the green part, okay, it's not done yet. You need to wait for acknowledgement on the left hand of the green part. Okay, in that case, you can kick out from the stream. Otherwise, you have to hold them. Okay, so the data is still in the buffer. But if it's after timeout, you still don't receive a ACK, you need to resend. Okay. And otherwise, you just send the data. what does this mean? Right? So you don't have much available data. Okay, if you always have available data, so you don't want to hold it, right? So you don't want to hold it for 1 hour then send. Okay, right? You want to hold it until you have MSS start, then you send it in batch. Okay. So here we will send a non-full packet. Right? We will try to send a full packet as long as you have more data that come. Right? But if there's nothing happening, right, we don't want to hold it forever. We will send if nothing else is happening. Okay. If possible, we will send the full packet. We will not send it byte by byte. Okay. So this is the Nagel algorithm that delays transmissions. Okay. So you can see there will be delay in transmission, but if you keep having some data sending, then you will finally efficiently pack this segment, 4 segments packet, okay, and you can send out more efficiently, minimize the overhead on the head, amortize the overhead. Okay, so but there's a cases that you don't want to delay, right? Why I wait for 10 milliseconds to send? I want a instant message, right? So like I just want to say hi, okay? You don't delay me 1 second to have enough data to send. Okay. If that's the case, you can achieve that. So if you remember, in socket programming, we can set a flag. Okay, we send for no delay. If that flag is set, remember in here we have the flags. Right? If you can, network interface card see that flag for no delay is set, it will immediately send it without a wait and buffer them until you have a four packet sent. Okay. So basically, you can write things byte by byte. But down there, so they are running the Nagel's algorithm, where it will batch your data and finally send in one batch, okay, as much as possible. Of course, it will not wait forever. And if you really don't want to wait in any way, you just set the flag, the TCP no delay flag. It will send immediately. Is this okay? Any questions? Okay, if no question, we will move on. Okay. So we also need the functionality for error detection, right? So if you remember, we have a field called checksum. So checksum is here, okay? So checksum detects packet corruption, okay? And it will not detect all packet corruption, right? Because it can happen that the two summation cancel each other, right? Because one bit is the 1, another bit is 0, but they are both flipped. 1 plus 0 and 0 plus 1 is still 1, okay? So it can detect some packet corruption, okay? And remember in IP datagram, we also have the checksum, right? So TCP also has that, okay? It's kind of redundant. That's why IPv6 removes that. IPv4 still has it. So this checksum is computed over IP header, TCP header, and the data. Okay? And if some bit is flipped, then the checksum will not match your new checksum that computed on the receiver side. And also, sequence numbers can catch sequence problems, right? So this was not a concern, if you remember, in our UDP, right? So in our UDP, we talked about, let me see where it is. Right? It does not detect dropped, duplicated, and reordered packets. This is not an issue if it's not a stream, right? But now we have a data stream. Okay? Then this really matters. Okay? So we can get duplicate packets, right? So, but that's fine because we already got a sequence number, let's say 123. Then I got another 123. It's the same packet, right? The same content. We just ignore it. This can happen because, for example, the packet somehow gets stuck on multiple slow routers because their queue becomes full. And unfortunately, that causes a timeout. The sender sends another packet, right? So then in that case, you have 2 packets that are received with the same content on the receiver side. And with the sequence number, you can safely ignore the duplicate one, okay, that you receive later. And we can also tolerate so-called out-of-order packets, right? So because your packets may be sent as packet 1, 2, 3, but receive maybe the 3rd packet to receive first, because the first 2 maybe get stuck somewhere, okay, or get retransmitted, right? Because maybe packet 1 sent and unlucky that the 4 queue in some router, 1 gets dropped, and 2 and 3 arrive, right? So that's reordered, okay, because then you retransmit 1 and 1 is received later than 2 and 3, okay? So this can be easily detected because you have the sequence number, you know where they are, right, in the stream. Okay? So you can reorder them and piece them back into the stream and put to the top level application. And so also you can detect whether there's a missed sequence number, right? So if something is missed, you will know it. Okay, you will know, hey, segment 3 is not received. Okay, even though I received 4 and 5. Okay, I will ask. So you know, so the sender will retransmit that. Okay, because that sequence number acknowledgement is not received. Okay, the receiver can even ask for retransmission using NAC. And so lost segment can be detected by the sender. So it's here mainly by receiver. Okay, by the sender, you can use timeout. Right? If you don't receive an acknowledgement of that packet after a certain time, that is unreasonably long. Right? Then you will do retransmission. You think that's missing. Okay? Because sometimes the router will not give you any information, just drop it because it cannot handle that part. The queue is full. Okay. So in that case, you need to, but in order to do that, you need to estimate the round trip time. The RTT is a round trip time, which means you send and acknowledge back this time. Okay. So you need to estimate the RTT to collaborate timeout. Right. So for example, if your round trip time is, let's use some large numbers, which in reality should be maybe 1,000 times lower. Okay. Let's say your round trip time is 1 second. Right. Then you can wait for maybe timeout, wait for 2 or 3 seconds. Then you say, hey, it's timeout. Okay. But instead, if your round trip time is somehow very long, 10 seconds, then it's unreasonable to set 3-second timeout. Right. You don't even deliver things to the other side and get an acknowledgement. How can you say, hey, it's lost? Right? So you should have multiple times RTT, maybe 30 seconds. Then you think it's lost. Okay? So for this purpose, we do need to estimate the round trip time to set the timeout. Okay, a reasonable timeout. Another thing is that the sender must keep copies of all data until acknowledgement, right? So which means, like we see here. Okay, let me see where it is. History. Yeah, here. Okay, right. So once it's acknowledged, you can free them out of your buffer. Right? But with send, you need to keep them because who knows whether it will get acknowledged or not. Right? It may get dropped. Okay, if that happens, then you have to retransmit it. And so that's what we are talking about here. You have to keep them until you acknowledge. Then you can slide the window forward. The old ones can be kicked out. Right? And so another concept that we will see a lot is called RTO. Right? Called the retransmission timeouts. Okay. So that's basically the timeout structure for retransmission because you think it's the original packet lost, I retransmit the same packet again. So RTO, if we see RTO, we should know that it's the timeout structure, right? And the RTT is the round trip time. Timeout structure should be longer than the RTT, okay? Just to safely determine whether it's really lost or it's not yet arrived. Okay? So the problem is that timeout linked to round trip time. Right? So for example, if you initially send a packet and then it's lost, right? And you wait. What we will do here is that we will wait for the timeout RTO, okay? And then we retry, which means we retransmit the same packet, and then we wait for the timeout, okay? So this thing can get quite messy if you think about it. RTO is short, right? So think about it. If you say hi and the other party come back say hi, and this time takes, let's say, 1 second. Right? If you retransmit immediately, even less than 1 second, okay, then you will never get a successful packet. Right? You always you are not patient, right, to wait for the needed time to get back. Okay, then you will just retry, and it will become a packet store, right? It will keep retrying, sending the same packet again and again. If you send many packets, it will be catastrophic. Okay, so the RTO should really be long enough. Okay, if timeout is too short, that's unacceptable. Right? You are doing necessary retransmission. But what if the timeout is too long? Right. So you think about, right. So this is so here we are not continuing. What if timeout is too long? Timeout too long is fine. You will not have this issue, but you will wait a lot of time, right? So if you already wait for 10 times the round trip time, right? You know that you say hi, another person should say hi back in 1 second, okay? Now you already wait for half a minute, right? So then you say, hey, I should say hi to that guy again. That's way too long, okay? It will delay the recovery time if you really have a packet loss, okay? So the RTO should be longer than RTT, but not too long, okay? So how do we estimate RTT so that we can set a reasonable RTO, right? So that's so-called round trip time estimation problem, okay? So the original, TCP round trip estimator works like this, okay? So it's using a so-called moving average, right? So if you know the stock curves, right? So they will do some analysis, right? So they will use a so-called moving average, 7-day moving average, etc. Right? So what it does is really, hey, the last time you receive the last packet that you received, that's the old round trip time. Okay, this could be this old round trip time is actually also a moving average till the last moment. Okay, now you receive a new sample, right? The next packet you receive. Right? So this is the new round trip time. This is the cumulative old round trip time using moving average. Right? So how do you update the current round trip time estimation? Right? So you will time alpha with old one minus alpha times new. Okay, so this is called the moving average. The benefit of this is that it's a unbiased estimation, right? Because if both are estimating the true thing, then using expectation, it's still that value. Okay. Another thing is that you can see this scheme is good because it's exponential decay. It's old value. If you continue, let's say this is RTTI, right? This is RTTI minus 1. RT minus 1 can be further expanded as this formula, alpha times RTT minus 2, etc. Okay? So you can see the longer time is, you have 2 alpha. Right? It's exponential decay. Alpha is usually less than 1. Okay, so if it's like 0.1, the next one is 0.01. Right? So the longer the time, the smaller the weighted place in your RTT estimation. It's really the most effective ones are the closer ones. Okay, so this is a very, very smooth and stable estimation. Okay, but again, so you want a smoothing, you adjust the alpha to be larger. Okay? Of course, it can not go beyond 1. And then your update is slower, right? So your reaction is slower to the new samples because this is going to be small wave. Your inertia is very low. Okay, so alpha is really set to a large number, right? Like 0.875, because maybe there will be some fluctuations in RTT, right? But overall, the network is relatively stable. You don't want to suddenly change this new RTT estimation to be very different, right? Because this RTT guides your RTO, okay? How long you time up, okay? If it's just a sudden change, then you significantly change your RTO. That will cause a lot of issues when finally to get back to the wrong the correct RTT. Okay, so that's the concept. So we will play safe, use a big inertia. So in reality, we just set RTO to be twice the running average of the RTT. Okay, this is already very conservative. But TCP is really already conservative. Conservative in the sense that, hey, if you can get back to in 1 second, but I will say, hey, if after 2 seconds I haven't heard a high, I will resend again. But not 1.5, not 1.3, it's 2 times. Okay, it's already very safe. Another thing is that the alpha is a big number. Okay, it really have a smoothing effect. Yeah? Consider a period of history to be stable. And so there's also so the RTT sample ambiguity, right? So what we are talking about here is that, let's say you initially send some stuff, right? And then, let me see. Then it times out, okay? And then you retry, and this time, right? This time you have a sample, right? You know the round trip time for the latest data, okay? So this is okay, right? So this is a new sample data. But on this side, what can happen is, what if your RTO is set too short, right? Because suddenly, let's say suddenly your round trip time increases a lot. Right? So You need to adjust RTO to be longer, but right now it's short. Okay, in that case, you think, whenever you get an acknowledgement, you think you get a success, right? Because this packet is lost, I will think, hey, the beginning time is this time, right, for this packet. The ending time is this time. So the actual round trip time is for the packet is this one. But I'm thinking it's this one. Okay? Now this sample is apparently wrong because it's too short. Right? You just retransmit it and you get an old ACK. Okay? So that will mess things up because we are using this sample. We're using this sample to update the running time. If it's suddenly a very short time, then it's just get messed up. Okay. So the way to handle this is really, we set a rule. Okay, it's just a set a rule to be safe. So this is the cont algorithm. Ignore samples for retransmitted samples. Right. So what we say is that, hey, if you have a sample, right, but it's actually retried. Okay, then I don't even consider this sample or this sample. Okay? I just ignore it. Okay? I think this acknowledgement originally. So similarly here, if you retry, even this sample will not consider. Because this acknowledgement is coming from the retry. You never know whether it's the retry acknowledgement or the old sample acknowledgement, even though it has some retry, because there's an ambiguity. So I don't even count them. Okay, I only count that RTT is initial send and successfully acknowledged, and my RTO is longer than that. Then it's a successful sample. I will take this as a sample to update RTT. Any questions? Okay, so if that's the case, so I think we don't have enough time to start another slide. We will have a quiz for today. So let's take a quick attendance. Okay, and then we will, let's quick attendance.
What can we work out? Yeah, can we work out anything? But she was just absolute on it. Is there anybody else that Sarah likes to sing with?
Sarah's pretty particular. We're really good friends. She is pretty particular. What we can do, my suggestion would be to ask her, give her that freedom to choose a partner. It'll be a problem.
So I think
so we need to give her that freedom to choose and also as music director. That would be the
Hello, Rachel Hayden. Your microphone's unmuted.
Yeah, so I just handled that. Okay, let's take a quick attendance.
My man.
Prince Banga.
I'm here.
Okay. Alex.
I'm here.
Okay. And Alex again, but Alex Connell. Alex Connell. Alex Connell. No. Oh, I see a chat. Maybe it's in the chat. No, it's also not in the chat. Well, Diego?
Here.
Okay. Michael? Michael Hunt? Michael? No. And I just see, right, so in the chat, so yeah, it's fine. Stephanie, I think asked for a lead. I remember that. Daniel?
I'm here.
Okay. Preet?
Here.
Okay. Andy?
I'm here.
Okay. Jack? Jack Sanchez?
Present. Hello?
Hello. Oh, I see you. Yeah.
All right.
What? What? Are you here? What's Stepano? What? No? Okay, so let's quickly go to the next list and then King?
I'm here.
Okay. Matthew?
I'm here.
Okay. Ebony?
Here.
Okay. Lawrence?
Here.
上司? 上司?
Yes, Professor, I'm here.
Ashley? Ashley? Ashley Chuan? No? Okay, so that's all for today. Thank you, and I will share the video on YouTube, and I will also release the next week. Okay. I didn't record for your name. Okay, so it should be fine. Cash. No worry. Okay. And any questions? I will be here for 1 minute. If you have any questions, feel free to ask.
When is the final gonna be?
Final?
Yes.
Yeah. Let me check the time. So basically, you know, for any course, we have the final UAB final schedule, final exam schedule. Let me check. So because we have to follow the time. Okay. I think it's probably this one. And then you can look up. So for example, our course is what's the course code? I think we should have a course code here. Anyway, so if it's like a Monday, I will check because we have 1E4C this kind of code, right? So who knows what is this code? In previous years it's there, but this year it seems that the course code is totally changed. Let me check and I get back to you. Okay, so I will let you know what's the time. But usually it's in that week, April 27, April 28. It's kind of it's okay.
Okay.
Yeah, I will let you. I will send an announcement. Thank you.
Okay.
So because we have the designated time slot, okay, we have to follow that. Even for those time slots is designated, we don't have the freedom to choose. But we can reschedule if you don't work out with any student.
Right. I was just asking because I know they're having the graduation April 30th for master. So
I see. So just send me.
And I'm just trying to see.
Just send me an email if it doesn't work out. Okay, we can make a accommodation accordingly. It's okay.
Okay.
Yeah, just remind me. Okay, so before the exam, so that we.
Okay.
Yeah. So quiz for transport layer. Yeah, we will make it available. Okay, today. So for ideas question. You're welcome. Any other questions from the students? Yeah, for the quiz, actually, it's a combination of what we covered in this lecture and also the circuit programming. Okay, if you still have memory of the circuit programming, you should be able to answer those questions. Okay. All right, I don't see any new questions, so I will end this class, and I will see you on Wednesday. Thank you.